Welcome to The Explainer. Today, we're jumping right into a concept that, honestly, sounds a lot like science fiction, but it's actually the invisible wave calculus powering the next generation of modern technology. You know, we hear a ton about quantum computers and quantum sensors, and usually it's all about superposition, right? That mind-bending idea that something can be in multiple states at once. But here's the thing. Superposition alone isn't the magic ingredient. The real secret sauce, well, it's something way more dynamic.
To really wrap our heads around this, we have to ask a simple but absolutely profound question. How do quantum computers actually find the right answer? Think about it this way. Imagine dropping two pebbles into a perfectly still pond at the exact same time. The ripples spread out, and right where they collide, something fascinating happens. Where two wave crests meet, the water rises higher, they amplify each other. But where a crest meets a trough, they flatten out and just cancel each other completely. You've actually probably experienced this yourself if you've ever worn noise-canceling headphones. They play an anti-noise wave that perfectly cancels out the background hum of an airplane cabin. That physical concept, right there, is called interference.
Okay, let's dive into this. Quantum interference is basically the phenomenon where the probability amplitudes of quantum states combine. They either combine constructively to amplify an outcome or destructively to cancel it out entirely. See, if you were to just put a quantum computer into a massive superposition of all possible answers and then measured it, you wouldn't just magically get the right answer. No way. You just get a totally random, honestly useless result. It's actually quantum interference that steers the computation. It suppresses all those incorrect answers and dramatically amplifies the correct one.
So here's our roadmap for today's explainer. First, we'll look at nature's invisible wave calculus. Second, sculpting probability and algorithms. Third, advancing next-gen tech discovery. Fourth, optimizing global supply chains. And finally, number 5, taming the quantum waves. Section 1. Nature's invisible wave calculus.
At its most fundamental level, the quantum realm isn't described by solid, deterministic values. Instead, it's all about wave functions, these complex-valued probability fields. Now, in our everyday classical computers, probability is pretty straightforward. A classical bit might have, say, a 50% chance of being a 1 and a 50% chance of being a 0. If there are two independent ways to get an outcome, you just add the positive probabilities together, right? They always go up. But quantum probability? That's a whole different type of creative arithmetic. Quantum systems deal in amplitudes, and these can be positive, negative, or even complex numbers. So this means if there are two paths leading to a wrong answer, one path can have an amplitude of +1, and the other can have an amplitude of -1. Add them up, and they sum to exactly 0. The wrong answers literally annihilate each other.
And this brilliantly illustrates the concept. What we're looking at here is a representation of the classic double-slit experiment, which really is the absolute heart of quantum mechanics. When you shoot quantum particles toward a barrier with two slits in it, they don't just form two distinct blobs on the wall behind it. Instead, notice the striped pattern in those fringes? They form an interference pattern. The particle basically exists in a state of probability, traveling through both slits simultaneously, and its probability wave actually interferes with itself. It's just a striking visual representation of how possibilities can literally collide.
Moving on to Section 2. Sculpting probability in algorithms.
So the big question is, how do we actually tame these subatomic waves to compute something useful? How do we get from a striped pattern of light in a lab to world-changing software? Well, the renowned computer scientist Scott Aaronson hits the nail on the head here. He says, the goal in quantum computing is always to choreograph things so that for each wrong answer, some of the paths leading there have positive amplitudes and others have negative amplitudes, while the paths leading to the right answer reinforce. I mean, really think about that for a second. You aren't just writing lines of sequential standard code. You are composing a choreographed symphony of waves. You're deliberately engineering an interference pattern so that the correct answer just leaps right out at you.
And this is absolutely crucial. This is exactly why quantum computers can be exponentially faster. Take Grover's algorithm, for example. It's designed to find a needle in an unsorted haystack. Classically, you'd literally have to check every single item, one by one. Tedious, right? But Grover's algorithm uses interference. It puts all the possible items into a superposition, and then it uses this thing called an oracle to flip the phase of the correct answer. Basically, it turns its wave upside down. Then, through a diffusion process, it creates this massive interference event. All the wrong answers cancel each other out, and the right answer's amplitude is massively amplified. Boom! It finds that needle in the square root of n steps. That is a total game-changing speedup, and it's powered entirely by interference.
Then, of course, there's Shor's algorithm. You might know this one for its ability to factor massive numbers and, well, potentially break modern encryption. Shor's uses something called the quantum Fourier transform. Honestly, you can think of it kind of like a musical prism. If you have a really complex chord made up of many different frequencies, the transform isolates the pure tone of a hidden rhythm or period within all that math. By using constructive interference to build up the paths that resonate with that specific period and destructive interference to cancel out all the rest, Shor's algorithm achieves a massive exponential speedup.
Let's move to Section 3, Advancing Next-Gen Tech Discovery, and see how this builds from the micro to the macro.
Because interference isn't just theory for quantum computers, it's the active engine behind some of the most sensitive instruments we have ever built. Quantum sensing and metrology are already completely reshaping tech discovery. For instance, we have SQUIDs, superconducting quantum interference devices. They use this exact wave collision principle to measure infinitesimally small changes in magnetic fields, which helps us out in everything from geology to navigation. Then we have atomic and optical clocks. They use highly stable atomic resonant frequencies to keep the ultra-precise time that our global GPS and financial trading systems rely on. We even use squeezed light, which is a specialized interference technique, to boost the sensitivity of LIGO. That's what allows us to literally detect gravitational waves from deep space. And over in the pharmaceutical world, mimicking these exact quantum wave interactions lets us simulate complex atomic molecular structures, which is massively accelerating drug discovery.
Section 4, Optimizing Global Supply Chains.
Now, what's really interesting about this slide is how we aren't just stopping at the microscopic or the cosmic levels. Think about the sheer massive scale of global supply chains. We're talking about routing thousands of cargo ships, scheduling entire fleets of trucks, and allocating resources globally. These are absolute combinatorial nightmares for classical computers because they have to evaluate every single route serially, one after the other. But algorithms like QAOA, that's the quantum approximate optimization algorithm, and quantum annealing, they use interference to evaluate vast solution spaces simultaneously. By parallelizing the evaluation and continuously adjusting the quantum state so it naturally falls into the optimal solution via interference, these quantum systems can slash computational time. We're talking about drastically reducing shipping costs and totally untangling global logistics.
Finally, Section 5, Taming the Quantum Waves.
Of course, I have to point out, if this were easy, we'd all have quantum computers sitting on our desks right now. The biggest hurdle we face is a concept called decoherence. You see, quantum interference is incredibly fragile. Remember our perfectly still pond from earlier? Well, the real world is incredibly noisy. Heat, electromagnetic radiation, even stray cosmic rays, they all act like random rocks being violently thrown into our pond. They disturb the waves and scramble that delicate interference pattern before the calculation is even finished. And when that happens, it causes the quantum state to just collapse back into a normal, classical, probabilistic system. So taming these waves, whether that's by building robust error correction or isolating qubits in extreme vacuums at temperatures colder than deep space, that is for sure the defining engineering challenge of our time.
So, we leave you with this thought to ponder. We've seen today that quantum interference isn't just some weird quirk of physics. It really is the guiding hand that steers quantum algorithms. It's the invisible wave calculus beneath the code that gives these machines their unprecedented power. We are quite literally learning to conduct a symphony of probability. And if we're already using this to detect gravitational waves, untangle global logistics, and simulate new life-saving medicines, what limits of the universe will we break when we finally, truly master the symphony? Thank you so much for joining us for this explainer, and as always, keep questioning the world around you.